Hi, everybody. Thank you for joining this PyData Global 2021 workshop. I'll keep it brief. I've just done some of the basic housekeeping before I started this recording. I'd like to introduce Nabanita Roy, who's going to give us a great workshop on getting started with text analysis. Nabanita, I'll hand over to you straight away. Okay.
Thanks, Kevin. Everyone, welcome to this tutorial on text classification. In this tutorial, we'll be looking at how to predict if a tweet is about natural disasters. Before I start, a little bit about myself. My name is Nabanita Roy, and I am a data scientist at ECI Worldwide. I really like natural language processing, and I really play with these kind of techniques. So here I am with this tutorial on getting started with text classification. We're going to look at supervised classification only in this tutorial. And so let's begin. So in our agenda today, the first thing that I'm going to do is run through this PowerPoint presentation, which lays down the basics of text classification and text analytics. And after that, when we look into the notebook, we will be using Python. You'll find the Python libraries which are required for today's workshop lying down in requirements.txt in the GitHub repository that I've posted there. And here's the list once again, if you want it. Before we begin, you could start installing them. In the workshop, we will look a little bit about the data set. This is a bit of a tricky data set because this is about tweets, and tweet texts are a little bit tricky in terms of text preprocessing and analysis, and we'll see why. We'll look at some basic exploratory data analysis, some text preprocessing techniques. Then we will be training a binary classifier, and then we will be looking at some model evaluation techniques for classification tasks. So let's begin with the basic question here. What is natural language and what is natural language processing? Natural language is anything that we talk, write, or express as a human, and leveraging the modern technologies for processing these expressions, the expressions that we do as humans, is natural language processing. And NLP, where does it fit in the EI ecosystem? Natural language processing is essentially an interdisciplinary subject wherein disciplines like computer science, technologies, mathematics, statistics, and you would require expert knowledge of the computational linguistics and behavioral sciences. So all these different domains come together and form the natural language processing domain. So it's fairly interdisciplinary in nature. There could be essentially, when you think about a natural language processing task in an industrial setting, you might want to accomplish a technology goal, and in a research perspective, you want to achieve cognitive goals. So technological goals mostly are when you want machines to do something like text extraction for analyzing social media for, say, indicators of real disasters, like what we're going to do now. Maybe look at some reviews on Amazon, and as a company, Amazon might want to see what is the general response to a particular product that they're selling on their website. So these are fairly achievable using our latest technologies. A little bit more advanced version of natural language processing applications is making a machine work or listen or act like humans. So what happens is because our styles are so different, so even me as an individual, I would text on WhatsApp in a different way, or I would write an article, or even when I'm talking right now, it is a different style. And the whole the entire thing, if we want a machine to work like a human, that whole objective becomes a bit more complicated. So it's a bit more difficult to achieve. So in this workshop, we will be definitely looking at a simple technological goal of just text classification using supervised machine learning. So what is text classification and what is supervised machine learning? So text documents can come, you might want to look at text documents on the internet, and you might be able to, as humans, understand if they're, for example, if you look at sentiment analysis, if they're positive or negative in nature. If you're looking at news article, you might understand if it's about, is it like about politics, is it about business or finance, or is it about sports? So we as humans can do it intuitively, but when you want to train a machine to do that sort of job, where you've got different categories and you want to have a collection of text documents categorized into these different labels, that is called text classification. And using supervised machine learning means that you already let the machine know that what a text is about already. So you let the machine know. So if you're categorizing news articles, you let the machine know that some of these texts are politics, some of these texts are about business, and some of these sports are about sports. And after you've trained the machine learning model based on the news articles that the model has seen before, it tries to predict if an unseen text document that the model, a text that the model has not seen before, is about politics, or is it about business, or is it about sports. The other example goes as if an email is a spam or not. You might see in Gmail, some of the emails, they automatically get classified as spam. So that's one of the most common use cases of text classification. Every time an email comes in, an algorithm determines if it's a spam or not. Gender identification, if an article has been written by a male or a female person. Sentiment analysis, again, a very famous and widely used application of text classification using supervised machine learning. And it looks at user reviews and user sentiment, and it has been really essential component in a marketing industry. So when you talk about text classification, one of the important things that we look at, that we talk about as a term, is called target or a label. So the keys that you give a model to understand what that news article is about, or if a review is positive or negative. So those are called targets. The information that you provide, if it's positive or negative, ones or zeros, politics or business or sports. So for gender identification, a label would be male or female. For email, it could be a spam or not spam. So that is the word target and or label is going to be used repetitively in this tutorial. So let's begin with some text processing techniques today. So we will be looking at regex and text extraction. So the most elementary form of extracting information from text is regex, which stands for regular expressions. Essentially, you match a pattern with a text, and you want to extract a text that occurs according to that pattern. Sometimes you want to just find them and process them in a different way. Sometimes you want to substitute them, the text which matches a pattern, and sometimes you just you want to use them for new features. So regex is one of the most elementary ways. Even it could be used for tokenizations, where you match a pattern saying that for the letters which are occurring in between two spaces, extract those words, and those are the words that are occurring in a sentence. So that brings us to tokenization. So tokenization is a method in which you break down a whole corpus. So by corpus, I mean a collection of text documents. So if you want to analyze them, you really want to get hold of the basic units that are words or tokens, and breaking down a whole corpus into these simple units of words is called tokenization. Once you do tokenization, there are a few other pre-processing that needs to be done. So for example, you have to do case conversion. Case conversion is like you want to convert and the entire text into lowercase or uppercase. That's for ease of pre-processing. For example, if you say, so just in case, just if you want to take the example of tokenization, capital T tokenization, and if I've written down a paragraph about tokenization, that paragraph might contain small t tokenization. And when a machine learning algorithm looks at these different cased words, it'll consider capital T tokenization as a different word than small t tokenization. So case conversion is essential unless you're working on a particular use case in which the capital or the sentence case is essential. Then there will be noise because you're getting these texts from the internet or somebody's handwritten text. If those are the things you're scraping data from different languages, so it might contain accents, it might contain HTML tags, and it might also contain symbols and emojis from tweets. So these things needs to be removed and checked for. Contractions. So often when we write down in conversations, even in standard literature books, if you want to process bookish texts, then you will find I've, or it's, these kind of words, and these are called contractions. You might have to expand those contractions into I will, I have, it is. Stop words. So stop words are words like are, is, the, which occurs multiple times, or probably the most number of times in a document, but they do not contain essential information a lot. So these are called stop words. And you would mainly look for removing those, analyzing and removing them. Right. Then normalization. So normalization of text processing techniques, for example, for converting these for different versions of verbs. So for example, if you've got visited or visiting or visitor, and you want to just get hold of the root form of that word, you might want to use some normalization techniques. So there's stemming and lemmatization. Stemming is a crude rule-based approach for getting for removing prefixes and suffixes and just getting the root word from a word. And lemmatization is a little bit more advanced, which takes a few more semantic and syntactic information from the words. For example, parts of speech. So it understands if a token that we've passed in is noun, is a verb, or an adverb, and it processes it and gets the root form of that word. And this is mainly for standardizing all the different variations of the same word that occurs in English language or any other language. Parts of speech tagging and named entity recognition are text tagger mechanisms in which you want to tag if a word is a noun or a verb or an adverb or an adjective. And named entity recognition is also important to understand if a text contains a name of a person, If it contains a location, we will be looking at these few NER, so in abbreviation it's called NER. So some of those named entities in our tweet as well. You might also want to detect if there's any amount like financial amounts, $200 if it's written down somewhere, you want to extract that information. So you can do that using named entity recognition. You can extract dates, etc. So these are different text processing techniques, not limited to. There are many more different kinds of those, but these are the basics, and we will be looking at most of these in our tutorial. And this is a little bit of an example of how the tokenization and cleaning works. So if you see the first sentence there, I just saw Barack Obama in, I think I missed in over there. So I just see Barack Obama. So I changed the cases for Barack Obama to lowercase, and all the elements in the sentence, please don't consider in over there. So I just saw Barack Obama. They're all separated into 5 different tokens or words. In the next example, you see this one contains some HTML tags, say the P and P here. It contains an emoji, and it contains a symbol there, and contains an accented character. So you might want to convert this into a series of tokens like this, which will contain I will. So I've expanded the contraction here as I will see you soon, Mon Chéri. And yeah, and I converted the saw here to see. So that's again for standardizing, for normalizing a text word. So from here, so these are all about the basics of text processing. So we come to machine learning part of it. So if you're from machine learning background, you would know that machine learning learns everything from numbers. Machine learning is essentially statistical models, and you need to represent everything that you have in text into numbers. And that's essentially what we're going to do after doing all these pre-processing. We're going to take this bunch of numbers, we're going to take this bunch of texts, and we want to throw them, pre-process them, and convert them all into a series of numbers. For a machine learning model to comprehend part of it. So how do we do that? How can we represent texts into into numbers? So the most basic form of it is just counting the number of words, the terms that are occurring frequently. So that model is called bag of words, and a bag of words model does not take into consideration the position of the word in the corpus, but it only takes the frequency in which a token is appearing in the text. So the word bag here refers to an unordered list of words. So the order is ignored essentially. And it also allows multiple occurrences for getting it counted. So this is a pictorial representation of how this little text is converted into an unordered list over here, and it contains different words that occurs multiple times. And if you line them up here, count these vectors, if you want to count these numbers here, you find the number of times the words say 8, I, the, to, and they have occurred so many different multiple number of times. And if you notice, these are all the stop words which do not contain a lot of information. These are the words that we need to remove later on. And say for example, you want to see whimsical, times, sweet, satirical, adventure, genre, fairy. I think these indicate as like it is about a movie or a drama or a book. So if you might consider that if a word is occurring multiple times, that doesn't mean that that word necessarily contains a lot of information. So that's the bag of word models, where you represent a text into the number of times a particular token or word is appearing in the text. The other model here is called bag of words model, and this model takes into account if how many times the number of tokens appearing in a sequence. So unigrams are essentially just taking the individual tokens. For bigrams, it's taking 2 at a time. So this is a sentence. So when you're looking at count vectorizer, so this appears once, is appears once, appears once, and sentence appears once, and this is also appears one. And if there's in the entire corpus any other collection of sentences, if this is occurs again, the count for this is going to be 2. So you take 2 of the sequences sequentially appearing text at once, and count the number of times these 2 tokens have occurred sequentially in the entire corpus, and then get the count of those. And the last model that we will discuss is the TF-IDF model. The TF-IDF stands for term frequency inverted document frequency. So term frequency is essentially counting the number of times the words occur, but a drawback of that model is that it gives more importance to the tokens or words that appear more number of times, which is like we've seen, which is not necessarily the ones that contain a lot of information. So TF-IDF model, what it does, it penalizes words which occur multiple number of times, and it takes into account how many times the token appears in one document and also in all the documents. So it kind of normalizes the effect of the words which are appearing multiple number of times. So
yeah, I just think maybe it was like stop for a few quick questions there. We've gone through those 3 models. So if anybody has any questions there.
So I think there are a few questions here on the chat.
Okay, I didn't see any, but go for them if you see them there.
Okay.
Oh yes, you're right.
So I see the, do you have, you can't see the screen or the video stream? If that's an issue over there.
I don't know if that applies to everyone because I'm watching it fine. So,
okay.
Probably that participant, maybe just log out and log in again. Maybe that's the best thing I could say.
So I have a question from Tom. How does it work for languages other than English, which keep words the same and relies on word order? Some other languages, say Irish or Polish, modify the words quite a bit from the basic form. So this model, so there are other models which do take the sequence in a consideration, but this model, so like I said, the limitation of this model is it doesn't take the order in sequence in consideration. So if you apply this, you should be knowing that this is not going to take the sequence in order. For other language, even for English, I think even for English, the order is an important factor. I don't know which language for which a sequence would not be a factor. Say Irish or Polish, I'm sure if you're speaking them, they would have some sort of, they would have sequence, whatever language we speak. So these are addressed in other advanced models in which the order is considered, and they're mostly in deep learning or neural networks which consider them, and that is out of scope for this tutorial, unfortunately. And given how emojis are pervasive in everyday written language, should we not make efforts to capture them so we do not lose information? Yes, we should capture. So this depends on what your use case you're working on. So if they are like tweets or from social media, then yes, it's definitely worth processing those emojis. And there are different libraries which are there nowadays. I think I think it's straightforward as emoji, some Python library that does it for you. And it depends on how much effort you want to give into processing these techniques. So because they require a lot of computational power. So it's for you to decide what you want to keep and what you want to delete from there. So you might want to treat it as noise if they're not very important for the use case you're solving. So for example, what target or what label are you trying to predict? If those, for example, sentiment analysis for them, I would suggest to you that keep the emojis. They're very essential for it. But something like, classifying what a tweet is about in general, what a tweet is about. In those cases, I don't think having emojis would be much helpful. So in those cases, you can treat it as noise. I think these are a couple of questions there.
Yeah, keep going. So yeah. All right.
Cool. All right. So in the statistical models, the TF-IDF model is it does take into consideration the drawback of a count vectorizer or the bag of words model. So when you start working on the tutorial in Python, you will be addressing that as a count vectorizer, because that's vectorizing the texts into the counts of the counts of their appearances. And TF-IDF essentially normalizes them and it tones down the importance of the words which occur multiple times or most number of times, and also the words which appear very less frequently, and it boosts up the importance of the words which have medium counts. So the last part of this presentation is model evaluation for text classification. So when you've got these labels, for example, if you've got sentiment, you might label them as negative and positive. So the actual data set will have some texts which contain negative. I'll take the questions after I talk about this. Yeah, sorry. So in sentiment analysis use case, so for example, we'll have some of those texts which are positive, some of those texts which are negative, and that is what the machine learning algorithm will be trained on. And and then there will be a prediction set in which text will be labeled by the model, and we'll have an already existing set of labels on which we will be comparing the predicted labels and saying that, okay, so it was supposed to be positive, and the model predicted it as positive. So that's a true positive. That means that the model has been able to label a text that had positive sentiment correctly. And similarly, for negative sentiment, now the problem comes in when a positive has been misclassified into a negative sentiment one, or when a negative sentiment has been classified into a positive sentiment one. So this little chart that you have on the right hand side, this is called the confusion matrix, and it summarizes the number. So it compares between the actual labels and the predicted labels from the model, and that is based on the test set of the machine learning use case, where the model has not seen the actual labels and it's predicting on those unseen texts, and you get these the numbers in here. Depending on those numbers, you will be getting the accuracy, precision, recall, and F1 score out of these of the model, and these numbers are going to help you to evaluate how good your classifier or how good your model is. So looking at accuracy, so accuracy is pretty simple. Out of all the samples, how many of those samples were correctly classified by the machine learning model. So that's as straightforward as that. Accuracy can be tricky sometimes. So sometimes the number of, say, if you're taking the example of sentiment analysis, sometimes the total number of texts in the training set will not have as many instances as negative sentiments. So for example, in a data set, if you have 1,000 samples of positive sentiment and 500 samples of negative sentiment, that's like 50% less, and the model learns from it, and it learns that and so the probability of labeling something negative diminishes before the training itself, right? So that's called an imbalanced data set, where the labels are not balanced enough. So if there are 1,000 positive samples, it should at least have some 800 to 900 negative samples, or 700 negative samples at least. And only then the model will be able to learn from almost equal number of samples. Now, if when you're evaluating them using accuracy, sometimes it's called accuracy paradox, and accuracy will not be the best solution for evaluating that sort of data set, a model's performance on that kind of data set, because most of the times either it'll the true or negatives will fall, so it'll be nearly equal to 1 most of the time, because either the true positives or the true negatives are going to be almost equal to the number of the number for all samples. And for us in this use case, we will not be encountering that. So we just kept it fairly simple. So the next ones would be precision and recall, and these are looking at only the positive classifications, or just one set of classification. So precision is how many times, so precision is all about model's prediction and how precise the model has been in detecting the true positives among all the positives that has been predicted by the model. So amongst all the positives that has been predicted by the model, how many of them are actually positive? And recall is all about what the number of positive instances that has been correctly predicted out of all those which are actually positives. So in this chart, you can see precision is all about the predictions. So the true positives divided by the sum of true positives and false positives for precision, and for recall, the true positive divided by false negative, and the true positive for recall, and it's all about the actuals. And F1 score is basically getting the best out of the precision and recall, and it's the harmonic mean of these two metrics, and it kind of gives an overall picture of how well the model has performed in terms of the actuals and in terms of the predictions made by the model. So I can go back to the questions once, and we can start with the Python notebook now. Yeah, like I said that, so the ones which are occurring so that example that I have on bag of words is really small. So in a large corpus, what happens is these numbers blow up really high, and the numbers which do not occur much, they do not, those are also the ones which do not carry much information. So this is based on just a little snippet, but when you add more and more information, in those cases you'll find that words like whimsical, satirical, adventure, genre, which actually as a human as well, if I see this, I'll be like, okay, this might be about a movie or a drama. And in those texts where it got more and more information, these words might have such sort of an average count of average numbers of counts, right? And the ones like the stop words will have many occurrences, and the words they will not have any information, and the words which occur very less frequently, they would also be the ones which will not carry a lot of information. So it's always mostly about, the counts would be about the average over there, if you want to line them up in the order of counts. Thanks for the discussion. So I can stop the sharing. I reshare my screen. And if you could all get started with the tutorial, if you want to follow on with the Jupyter Notebook. So once you have installed them, just ensure that all the imports are fine, and we can just start working through the basics of it. So we'll be using pandas, we'll be using scikit-learn, we'll be using word cloud, NLTK, matplotlib, and Seaborn for plotting. Yeah, that's it. Contractions as well. Okay. So a little bit about NLTK. So NLTK is Natural Language Processing Toolkit, and it is one of the basic Python libraries which are available out there, which has different NLP techniques available in its API, and they're fairly straightforward to use as well. Once you've done that, you might have to download a few NLTK corpus for the word tokenized to work. I think you'll encounter an error and do whatever nltk.download functy those corpus. I don't think you would need them in Colab. Right. So the first thing that we'll use is pandas read CSV. We'll be reading the data train.csv. The data set is there in the repository itself. And then we will be checking the data. So if you look at this little snippet here, you see, because these are data sets. So this data set is about tweets. So these tweets have been scraped from Twitter, and they contain some HTML tags, some hashtags, mentions. It'll contain some emojis and symbols as well, some punctuations. Some of those have been cleaned out for us in the data set already, and some of those are still in there. In this little, so it contains 5 columns. One is the IDs; those are IDs of the tweets. There would be some keywords which are present in those texts. There would be a location from where the tweet was posted, or the tweet location as and how the users have entered in the tweet. And then the target. So the target saying whether that particular, so whether this tweet is about a natural disaster or not. So 1 means it is about a natural disaster, real natural disaster. And if it's a 0, it means it is not about a real natural disaster. So these use cases are used for disaster location and disaster identification for recoveries and stuff. So so in this data set, we have 7,613 instances and 5 columns, as we can see here. So we'll be doing a few EDA steps, looking at the data distributions. We'll be looking at the missing values. We'll be looking at the cardinality of the features and the targets. So cardinality means number of unique values present in a feature. So by feature, I mean these ID, keyword, location, text. These are the columns that we might use for training the model. So these are all features, and the target is a target or the label for our supervised machine learning use case. Okay, and so we'll be looking for missing values. So if there are missing values, then we might have to remove those from our data set. The number of times, what are the unique values present in these columns or features? What is the distribution of the target by keywords? So which keywords occur most for, say, the real disasters, which keywords do not have a lot of information about, a lot of tweets which are about a real disaster. The distribution of target by location, so which locations have a higher number of tweets coming in about real disasters. So these are a few EDA steps that we will be looking at today. So the first code is about cardinality check. So there are a few different ways of doing this. What I like to do is I just use a for loop and just take the length of each of these columns in the data frame and apply unique on it, and it gives me the number of unique instances there. So you can easily see that all the cardinalities are really high, and that is really expected because IDs should be equal to the number of instances in the data set. Keywords are, so the keywords could have been of low cardinality if maybe they were more, clustered together. But as you can see, the keywords have 222 unique instances, so it cannot be, it has higher cardinality. Locations have 3,000 unique instances. Texts have 7,503 unique instances. And target has 2 unique instances. So what you can do is, so I haven't removed these, the duplicate text from the machine learning model, but this is there in one of the future works that you can do, or you can remove these duplicates. And then because it is a binary classification task, so binary classification meaning that you would have only 2 target classes, so it's either 0 or 1. So that's the binary classification task. If it was a multi-labeled classification task, you might have more than 2 targets. So it could be 1, 2, 1, 3 or 0, 1, 2, however you want to label it. And then just wanted to take a look at the number of non-null values and the data types in the data set. And I see that text, ID, and target, there are no non-null values, whereas keyword and location have some some missing values. And here's a little plot to see which what is the distribution of the missing values here. So I just take the sum of the nulls and then divide it by total length of the data frame, that is the total number of rows, and get a percentage of the total, which gets the percentage of the number of missing values. So it seems that location has a higher number of missing values. So it's almost about 30% of the data set does not contain location information, and a very small number of percentage of keywords missing in the data set. So there are 2 ways of handling missing values. Either you drop all of them, or you want to fill them up with some sort of value. And so we will be retaining this information, and we will not be dropping anything. We will see if we can find anything, any way of replacing them, and not the keywords though. But remember, because we will be using these statistical models, and we will be looking at the number of times these the words that has occurred in the text, So these keywords are a subset of the actual text. So you will find, say, just a second. So you will find words like ablaze in the data set. So if ablaze was there in the keyword, then ablaze would also occur in the text. So in those cases, you basically don't need the information that is there in the keywords for training a model using the text, because ablaze will already be seen by the model in the text column. So we can easily drop keywords, but we want to still analyze the data before we discard it. So we will be keeping it. So you can see this word, so ablaze keyword is there, and it will also be present in the text here. So the locations, you can see there are different kinds of location here. You see just the city, and there's established when, capital letters, and that's not, that's like a continent. This is just a US city and the state. So there are different variations. There could be hashtags in the location, which is really messy. So this emphasizes on how difficult natural language processing is, and especially when you're looking at social media texts. I just wanted to check what's there in it. So you find, so there will be URLs as well in the texts. So what you might have to do, so for data analysis, you might have to go and print out different chunks of the data and see what sort of data is appearing, and what could be the anomalies present, and what sort of noise you might have to clean in it. The next cell is, I just like to standardize the column names so that I can just use it directly, these variables in my data set. So you can totally skip this when you're working on your own use case, but this is just how I prefer for my coding. So every now and then you'll see the df if I'm selecting a keyword. So I'll be using these variables that I have named here. So these are just coding practices. So the next thing is about keyword analysis. So the main questions that I'll be addressing is which keywords have occurred the most, and which keywords have higher percentage of tweets or are about real disasters. And it seems like this is also looking at the kind of keywords that has occurred here. So fatalities have the highest number of tweets in the data set, then deluge. And I think fatalities and fatal, these words occur here. So you can see fatal here, you can see fatalities here. And so you can see that there's a problem of normalization again. So you can use stemming on these, and you can reassess the keyword counts. And then radiation emergency and inundation threat, these are less frequently occurring keywords. Yeah, Armageddon is means something about apocalypse. And then I have, so whatever I have got there, I have again created another plot with hue on target. So the argument hue basically splits the data into the classes in bar charts, and I've passed in y as the keyword. So basically plots the counts of these keywords and separated by the target labels. So zeros are the ones which are not about real disasters, and ones are about those which are real disasters. And we check words like keywords, if it's aftershock, then those are not about real disasters. That's cannot be explained, but things like debris and derailment, and there's another one called wreckage at the bottom. So all the tweets over here, you see the gray bar is missing. That means there are no tweets which are not about real disasters. All the tweets which are all the tweets with keywords wreckage, derailment, and debris, they're all about real disasters. If you look at them. And then body bag, so it contains a percentage 20. So you can either, so I cleaned it, but then later on realized that it doesn't make sense to clean the percentage 20 because I will anyway be using these texts for cleaning, for model training. So these are basically, this is a process that I've taken to see the top 10 keywords for tweets about real data sets. So it's the bar plots here says that derailment, wreckage, and outbreak, there are the most frequently occurring, top keywords for tweets about real disasters, and it's fairly you can deduce that from the previous plot. And then again, I have taken the counts for the keywords only for about real disasters and ordered, which are not about real disasters, and sorted their values by the counts of the IDs. I did the same thing here. So when I passed in the data, I sorted those values by the ID and just took the first 10 out of it. And similarly here, when I plot this, I just took the first 10 out of it. And that's my plot where body percentage bag. So there are different versions of body bags. There's body bag, there's body bagging, and their body just simple bag, no bags. So those are a few cleaning processes that you can take a look at later on. And this is just an overall probability of appearances of keywords among all the tweets, and probability that if that keyword appears, then would that tweet be about a real disaster or not? So where derailment, debris, and wreckage have 100% probabilities depend based on the data set that we're working on. So, so the next thing we look at is target analysis. So before we proceed into target analysis, are there any comments there? No, okay. All right, so after we look at the keyword analysis, we look at, I looked at target analysis. So ID is used as counts. You could use any other field for counts, but ID, because it doesn't have any duplicates, and ID is just so ID has been used for counts because it's got all the unique values and there are no null values. It's just for counting. And the general purpose of this analysis is just to see what kind of data set is there. And before you train a model, you should know what data you have. And this is just a sneak peek into how you can conduct data analysis using texts. So the next thing that is important for training our model is, okay, yeah, you're grouping by and you're counting the occurrences there. And that's why I've used IDs there. Sorry, here. So the target, so we need to see, so like I talked about imbalanced data. So what is the percentage of data that's what is the percentage of the tweets which are about real disasters, and what is the percentage of tweets which are not about real disasters, that we need to assess. And here I have a percentage. So there 57% of the data set has is about it's not about real disasters, whereas 42% of it is about real disasters. So it's not that bad. So we can fairly ignore the problem for imbalanced data sets. So we don't have to really balance the entire data. Had it been really small, like if it would have been like only 1,000 samples of real disasters as opposed to 4,000 samples of not about real disasters, then we would have had to go for balancing techniques. So we can fairly ignore that here. And then just by location. So this is just trying to see what is the distribution of the target based on the location. Sorry, where the target is, in which location is not present. So this is just for checking, because I had a thought. I thought about if people are not posting their locations, it might be that a higher percentage of tweets are not about real disasters, and that's what it is seen here. Even though tweets which are about real disasters are catching up with it. But I would assume that if people are posting about real disasters, it would have some sort of location value in it. And then this translates from this one that, yeah, because anyway, our data for not about real disasters is higher than about real disasters. So it follows the percentage distribution here as well. So the target refers to human terms is as how you understand what is whether the tweet is about a real disaster or not. Target is basically just that that understanding if it is or if it's not. The target is understanding when you're predicting if it is about a real disaster, if it's not about a real disaster. Like for sentiment, is it positive or is it negative? So positive say 1 and negative would say 0. For real disasters, we're labeling as the targets or the tweets which are about real disasters are 1, and the tweets which are not about real disasters are 0. So that's our target, 0 or 1. And the target is for predicting. The target will be fed to a machine learning model from which the model will understand when it reads a text or tweet on one side, and it will map it with the given target on the other side, and it will assess the patterns which are there in all those tweets which are about real disasters and in all those tweets which are not about real disasters, and it will be predicting that target and giving a value back to us if it's a 0 or 1, based on which we will be able to understand what the model is predicting. I hope that makes sense. It's for us to infer from the data set what it is about. Okay. SNS does account by itself. You don't define y, right? It does, but you need to pass in the y or x. So you need to give some sort of value to understand which axis would it plot on. So x and y are for which of the axis. So here, for example, I've used y is equal to target. So it is for the y axis. So that axis, and this is the x axis. So whenever I use x, so here in this case, I used x is equal to target. So it knows that it has to plot the count on the y axis and the labels of target on the x axis. Similarly here. Problem. So then we look at the locations here again, and we want to see what sort of location is present. So you see all sort of gibberish data are present. You have some latitude and longitudes. You've got English words like news in the location. So it's not a very, like, it's not really standard. And just looking at the all those locations which are there in real disasters, tweets about real disasters. So this is a sneak peek. So this is basically for just generally getting an overview of what type of data is present. And you see there are cities and city state, city country, like here, and there's country name, country abbreviations. There's nothing standard in here, so it's not that straightforward to assess the locations. So and this is the top 20 most frequently appearing locations in tweets about real disasters. And this is without cleaning this. And the reason being, cleaning all these is going to take a lot of time. And I think you can go after the tutorial, you can spend some time in looking at how you could standardize them. So USA, United States, so you can create, what you can do is you can create a whole mapping system in which you could say that everything which is written as USA and United States, you can put them all into one category called USA, and you can create a dictionary about it and then map all of these different locations into it. You can also standardize the city, and you can extract just the state names and see if these state names occur in the collection of state names in the USA. The different ways of doing it, but it's going to be really time consuming if you attempt it. So the way out here, so when I was looking at this, so I saw that it's going to be very difficult and time consuming in order to do that. So what I did is I went back and I did some location tagging using named entity recognition techniques, and I applied that on our tweets and extracted if a location is present in the actual tweet body or not. Because if it's about real disasters, then I would expect those tweets to have a location associated with it written down in those texts when they were posted. So the next few things is just about some text data test where you will find. So this is just looking at the data and looking at these. So you find some mentions here and some gibberish data, some hashtags over here, some multiple punctuations. So we will have to remove punctuations and remove URLs from the text, HTML tags, mentions, and %20 from the keywords. So here with the basic cleaning, so we go into the text pre-processing. The first element that we learned about is regex, and using regular expressions, you can detect the pattern in which a string or text appears, and you can either extract them or substitute them. So what here, so I have used regex for substituting. So re.sub is for substituting input strings. And when that given string matches with the pattern that you have provided. So here I've written down a pattern for regex using this regex, and I will essentially remove them. I won't keep any of these URLs. So I just substitute them with a blank space, or with nothing, basically no blank space. So it'll just remove them all from the corpus. And this is basically the input text of the text string. So you can play around with this different regexes. So this is just for testing. I haven't yet created the functions yet. And if you think about it, so if a tweet is about real disasters, it might tag news channels. And if you lose that information of news, tagging the news channel, it could be an essential keyword for predicting if a tweet is about a natural disaster or not. And so I wanted to preserve the word news if it's occurring in a tweet or not. And that's something that I have to detect before I remove all the mentions. So this is the regex for removing the mentions from the tweets. So in the next cell, you'll find a list of functions. So these all functions does their specific jobs. So it removes the URLs, it removes the HTML entities. What could have been done is you could refactor them into just a function that takes in a regex, and it matches with the pattern and a given text. So you basically might not have to run, you might not have to write so many functions, but I wrote them to have these names in it, so that it's more user-friendly and readable for the demo. So then you can convert them into a lowercase. You might actually don't need to do that because you can just really call that function from the Lambda functions. So all these functions are created to support Panda's Lambda functions. So what it does, Panda's apply function. Yeah, the URL pattern is a fixed quantity. Yes, you fix it. You fix the pattern. You have to create the pattern. So there are different tutorials that you can find for creating regex, and you will have to fix it and pass a text with re.sub. And if you want to replace it with something, you'll find all the URLs replaced with something. And I haven't written anything, so it's just not going to put anything over there. So you have to create regex, you will have to go for regex tutorials in which you would be able to create more regex. So so if you go to DataCamp, if you're familiar with DataCamp, you can find more tutorials on regex. And you can also verify, so there are websites in which you can put down your regex and you can put a sample string and it'll do the tests for you. So it's just automated online UI as opposed to like Python code like this, but it does essentially the same job in the background. Yeah. So once I'm done with these, so again here, so if you see, so I used re sub and I used re find all as well. So regex find all, so finding all the types of punctuations that are appearing there in the text. So counting, yeah. For counting the punctuations and getting a length. So this basically returns a list. So get punctuation is going to be a list of punctuation. And if you get the length of it, you basically get the number of punctuation that was there in a text, the text that you pass in. And pre-processed text, basically, again, I use the regex substitute form, and what I say here is, if you find anything apart from so this sign says, if you find anything apart from the alphabets, digits, and spaces, then replace them all with basically nothing. So with this null, and you basically just keep or sieve out only the text, the numbers, the alphabets and the numbers out of it, and the spaces. So that's the only thing that you retain in the data set. You remove everything else. So basically you're removing all the punctuations from here, and you will be losing information on if there are any symbols. Oh, so you have to first, so I am not using emoji detection in this one. So if you're going for emoji detection, you will have to execute the emoji detection before you apply this cleaning of text. So you have to do it before it. So you see, pre-processed text is the last thing that I do here. And I have everything else done one by one. So this is a pipeline sort of a thing where you design and you prioritize depending on what you want to keep and what you want to remove and what information you want to extract before you remove some information. So when you remove noise, you always remove some information, and you need to pick and choose what information you want to keep. So if you wanted emoticons from the tweets, then you will have to do it before you pre-process this text and remove all the punctuations. And sometimes emoticons are also ASCII values. So you might, if you might want to use, keep that in mind. So before you remove hashtags and stuff, you might have to do it before it. So yeah, so I first removed the URLs, then the HTML entities. For pandas, this kind of command, you will basically, so what pandas does, it iterates through every text in the tweets, through every tweet in the text column, and it applies this function. So it automatically calls, so this could translate for each tweet in a column called text. So it basically calls remove URLs tweet. So for every tweet in there, it applies remove URL. So you don't really have to specify anything out of it over here as function, but you're basically calling this function for every tweet in the column text. So that is what I have done in all of these executions here in this cell, and it'll take a while to run. Regex1 is my favorite website to teach you about regex quickly with very short interactive lessons. Yeah, I haven't used Regex1, but yeah, I have used DataCamp, and I think any of those tutorials, if you start experimenting with it, it just becomes really easy. Yeah. Yes. For this use case, yes, right. It is a concise version of for loop, and it's also very faster. So if you use a for loop, it's going to take a very long time. So you can try and compare the time. You can time both of them. You can use a for loop on each of these tweets and apply any of these functions, and you time it with the apply function. You see it's going to be really much faster than using for loops. So so then last, we're just checking the training heads. We have created one extra feature here, which is the punctuation count per tweet. And we have replaced body, the percentage 20, which translates to a space. Yeah, so that's removed from the keyword section. And then I'll do a little bit of some punctuation analysis here and see, this is just exploring if there's any pattern which is existent in the number of punctuations which are there in real disasters, because you might think that if you're saying, okay, I'm safe, and you put in loads of exclamations when you're posting a tweet, so it could be possible that the real disasters might have a higher number of punctuations. But it's clearly opposite, where texts which are not about real disasters have really many outliers. So it has a longer distribution than real disasters. And about real disasters, they're more like concise. And then I checked, so I basically cleaned keywords. Did I clean the keywords here? So yeah, cleaning the keywords here, and then just taking a look at, so words like, when I was talking about text normalization, so maybe an example over here, demolish, demolished, and demolition, they could all go back into the root form, which is called demolish. So demolition is a noun and demolish is also a verb. So there could be, we might have to pass in the part of speech information to a lematizer in order to get that root form. And if you're using stemming, you might see just DEMOLI appear, and because it is a rule-based mechanism as opposed to a more advanced sort of machine learning sort of solution, it'll just blindly remove SE, SH, ED, or HED, and it'll just keep DEMOLIS or maybe DEMOLI. And then what happens is you lose some information over there because they're not real representations of the word, but you'll still be able to make them standard. So that's about keywords, and so we want to see if a tweet is about natural disasters, then you might want to see, you might see a lot of people mentioning the casualties, some sort of numbers associated in those about those disasters in the tweets. So here what I've done is I wanted to capture if there was some sort of number present in a tweet or not. So what I've done here is, so I've just did a regex find all. If it matches a pattern for numbers, then it gives me a list here, and I just see if there is a list which comes out, then I return a 1. If it doesn't have any number, it will not return anything, so you just return a 0 in that case. And so I constructed a bar chart here, and it's comparing the number of, if numbers are present or absent for real disasters and not tweets about real disasters and not about real disasters. And if you see in the tweets about real disasters, the percentage of appearance of numbers is higher than those in which are not about real disasters. So that's about mentioning a mention of numbers and tweets, and we go into sentiment analysis. Why we need to do sentiment analysis is because you would assume you're sharing some sort of negative emotion, or saying there was a terrible accident. So you would have a higher percentage of, you would assume that you have a higher percentage of negative sentiment expressed over there as opposed to positive sentiment. So in this one, we're using Spacey, and you might have to download these depending on what your setup is. So it does take a little bit of while. Let me know if your codes have executed the first 2 lines here, and if you have any problem in those. So yeah, so once it's done, what I did is, so I just called, so Spacey has its own, Spacey and text blob. These are 2 main natural language processing Python libraries. And Spacey has an integration with text blob. So text blob specializes Jyoti, I'll address your question later on, right, in the Slack channel, maybe. Thanks. So TextBlob is a Python library which specializes in understanding tweets sentiment, and it is given out by the polarity of a tweet. So that's the API that gives you that information. So what I did is applied that, and this is a Lambda function. So X here represents every iteration of the tweet over there. So it's more like for all tweets, which I have expressed as X here because I've used X here. Then get me all the NLP of convert X into an NLP object. So NLP is the object that you create from Spacey, and it essentially creates, understands and analyzes all the properties. It understands the tokens. It understands recognizes the named entities in it, the parts of speech tagging, and you don't have to really do it. You just need to convert the text into an NLP object from Spacey. And there, because they've integrated with TextBlob, you can just easily go for dot polarity. So you basically have to call that on it, access that attribute, and you get that value basically in the column called sentiment. So the Lambda function, what it does is it iterates through every instance of tweets in the text column, and it converts each of these tweets into an NLP object, and it accesses the polarity attribute from that object and basically stores for each of these corresponding tweets into the column called sentiment. And it will take some time to run. And then like I checked for location and numbers, I will check what is the distribution of the tweets about the disasters based on the sentiment, if it's positive or negative. So now sentiment, what the number that you're going to get from sentiment is a continuous number between -1 and 1. And if you can either binarize it. So this is how I have done it. So if the number that you've gotten from the sentiment polarity, if it is more than 0, then make them all ones. And if it's less than 0, then make them all zeros. And you can set a threshold depending on the use case that you're working on sometimes, because 0 is basically pretty much a gray area where the model was not sure if it's more positive or negative. It's more like a neutral region. So sometimes you might want to set a threshold if it's 0 or 0.1 that you want to set the binarizer to. It'll take some time and we can go back. So is there any more questions until it runs? No model named text Spacey blob. So I think you have to do this first. Can you try and do this first? All right, so I execute the binarizer and plot it around here. And so tweet length analysis is, again, if I'll just walk through what I've done, and we can stop at the data modeling pipeline building. So the tweet length analysis for any language text, sometimes keywords is an important part of analysis is about assessing how long or short a text is. So this is precisely what I've done here to check how long or short the texts are. In the sentiment, again, you can see if you go back to the sentiment analysis, the chart, the real disasters have a higher percentage of negative sentiment expressed than that of positive sentiment. And you can see the same for non-real disasters. It basically follows through the same original distribution. So still we're in a good line here. For tweet length analysis, I have plotted here a histogram of the words, the number of words that are occurring per tweet, and the number of characters per tweet as well. So they will basically go hand in hand, because the higher the number of words, that higher is the number of characters. You can also normalize them using different stylometric techniques. The next important thing here would be a word cloud. So that is one of the core text analytics tool for data visualization, where you use the Python library called word cloud to create a chart like this, which contains the whole set of words that you have in a data set, and you see which words occur more frequently. So what I've done here is, first I have divided the data set into two sets, one which contains all the tweets about natural disasters, and one which does not, the tweets which are not about real disasters, and I plotted them using the word cloud Python library. And you see in the word clouds for tweets about real disasters, the words new, fire, death, these are the words that are of bigger and bolder font. So these are the words that have occurred more number of times in this set. Whereas more generic terms you will find in the words in the tweets which are not about real disasters. So you can fairly distinguish that this has a topic which is disasters, fire, suicide bomber, you find spill, emergency, weapon, burning, wildfire, storm, these kind of words. Whereas this is more like, it doesn't have a specific topic associated with it. With the location analysis, what I've done is I just detected if there's a location associated with it or not, and I just plotted if there is an identifiable location in the tweet text body or not. You can execute it later and read the comments here. And finally, for the text data preparation, I will just be using the location information. I'll just be using the location information and the text, the tokenized text, and I will join them both. And that is what we're going to be training a model on. So in the model training pipeline, I'll let these these cells execute. So this is plain joining two columns, which contains textual information. That's it. You can easily do it in pandas. And once I've done that, I have created a few helper functions in this cell, which is just for printing the classification metrics and predicting the, this is not basically required for you. So I haven't predicted on the actual Kaggle data set, on the actual Kaggle challenge. So this is just for printing the classification metrics once you pass in the required arguments, which is the actuals and the predicted values. In the count, so there are two ways of using. So we looked at the bag of words model and the TF-IDF model. So for the bag of words model, you will be using count vectorizer. And for the TF-IDF vectorizer, you will be using this TF-IDF vectorizer from sklearn. And yeah, so the data set is all prepared. You can see all text. So we have all text here. And that is basically a tokenized version of location information and a text tokenized information. And then what we have to do is, because we need to pass this, so this count vectorizer always takes in a string as opposed to a list. So right now you can see this is in the form of a list. So we need to join them all back with spaces. And that's what I've done here. So all text joined, and I applied. So basically join all the elements in this list with including a blank space. So that's all I've done here. And then went on to create this count vectorizer where I have split the data set into a train and a test data set. Train and test sets where I have an X train with which I'm going to train the model, and Y train, which is the target for the training samples. And X test and Y test correspond to the test set of this data set, and I've split it by 20%. So 80% of the data set is result for training the model, and 20% of the data set is result for testing the model. And then I created a pipeline here, a column transformation using count vectorizer, which is basically going to create a matrix of all the words and the counts of all these words in the data set. And using that transformer, I will fit it on the X train, which is our training samples. And I will, after transforming, basically, you'll get a sparse matrix out of it. And if you see the shape of it, you see there are 53,000 columns in it. So basically 53,000, almost 54,000 features that has been extracted. That is the number of words that are present in this entire data set. And you see, this is really sparse. So that is one of the drawbacks of, of this sort of a model, statistical models, in which you take the number of counts of the vocabulary. So there are different ways of minimizing the vocabulary. And you can, I can forward on some links to go through such tutorials. And once you've got this feature, so basically you've converted everything that you had in text into numbers right now. So these are all the counts of the number of words appearing. And you basically will be passing all this entire matrix to the logistic regression function, so which is a machine learning model that I will be using for this tutorial. And for fitting it, you will need this the sparse matrix and the corresponding labels or the target values, and then just fit it, predict it, and you get the predictions on the test set. So this is the data that which is unseen by the model, and this is the data which is seen by the model. And so the training prediction and the test predictions are stored. So basically you get a series of zeros and ones depending on what the model thinks this would be. And I think I did not execute this. So once I print this, so I'm basically passing on the training predictions, predictions on the test set, and also on the training set. So you see the train, if the model is evaluated on the data that it has been trained on, you see the accuracy is really high. The F1 score is also very high. That means the performance is really good, and so it indicates that the model has been overfit, or it learned very too hard from the data it has been given out. And you see the performance on the test data is less than that which is from the training accuracy or the training F1 score. So this shows how a model could overfit because of statistical NLP techniques. And then similarly, I've used TF idea vectorizers. This is just the naive term frequency counter, and this is normalized over all the documents. And using the same ways, I have trained a model using the X-train sparse and Y-train. So this is a sparse matrix that is being generated by transforming that model, transforming the text data into its TF-IDF vector form, and then passing on the labels, and then predicting on the similar form of logistic regression, and then evaluating the models here. The accuracy have gone down a little bit. And I would think this is because the individual texts are of really short length. So if and also the data set is not very large. For larger data sets, TF-IDF is a better option than count vectorizer. And lastly, this is just an experiment for helping you out in checking different sort of models. So you can basically pass in a list of models, and you can create everything that I've written here in Python into a specific function and iterate through different models with its default parameters and see how it performs on these data sets. So the logistic regression is the best option here according to this report, because it has the highest number of highest accuracy and F1 score. Multinomial NB is in the second position, and decision tree classifier hasn't performed really well, and that's mostly because this is a really sparse data set, and decision trees are not well equipped to look at such sparse data. So the performance of decision tree or any other ensemble methods will not be as good as the probabilistic models like logistic regression and multinomial NB, because counts are essentially giving out an impression of the probability of the words occurring in a text. So these are probabilistic models are more related to the idea of TF-IDF and back of words model. So hence their performances would also be better than ensemble methods for classifiers. All right, and then there's some list of future work, and I think I'm done for the tutorial. Sorry about rushing through the entire thing. You can be in touch with me on LinkedIn or on the Slack channel, and we can resolve some questions that we have from this tutorial. Thank you.
Great stuff. Thank you very much. So we just went a little bit on, but I feel it was worth it. It was an extra 10 minutes. Thank you, Nabanita, for that great tutorial. And well, hopefully everyone in the audience has learned a lot, and that you'll be able to use this and grow as a data scientist. So again, just like to thank Nabanita, but also to thank
you very much.
all of you who've attended and all of you who contributed to making this a really good session. We hope you enjoy the rest of the conference. That's it, I think. I'm going to leave the recording there. We're going to have the recording up on YouTube eventually, not immediately, but eventually. I'm going to stop the recording now. Thank you very much, everyone who's watching us on YouTube.
Thank you.